This episode is sponsored by Brilliant. Everyone always talks about colonizing Mars and toning it green, but Venus might turn out to be a far better candidate for terraforming if we can just cool it down first. Last month we talked about terraforming Mars and how to warm it up and thicken its atmosphere to bring springtime to Mars. Venus, our other close neighbor, is something of the reverse case. Mars and Venus, our first two big targets for colonization, have almost the exact opposite strengths and weaknesses. Often Mars is seen as the most logical first target, which can seem strange on reflection. It's farther from us than Venus, our launch window's to it just once every 26 months, whereas Venus is every 20 months, and it's a closer and more direct shot. Venus is also much bigger than Mars, with a surface gravity nearly that of Earth. Venus has plenty of light and atmosphere to work with. Indeed, we thought it was probably a paradise world well into the 20th century. The problem is, it's a scorchingly hot hellhole. Cool it down and it would be practically ideal for terraforming, with just one other big problem. It spins very slowly. By weird coincidence, Earth and Mars have near identical day length, just 37 minutes longer on Mars, a little extra sleep, and nothing in the solar system comes close to that. The next closest is Uranus at 17 hours, and the various moons and asteroids almost all have either very long days from being tidally locked to their planet, or very quick days of just several hours. Venus, though, takes this to extremes. Unlike some objects whose day and year are the same length from being tidally locked, Venus's rotational period is actually longer than its orbital period because it spins backwards. And while we're not sure why it's such a blisteringly hot world, beyond its proximity to the Sun of course, we tend to assume Venus spinning slowly and backward is related to its monstrously high temperature. A couple years back we looked at colonizing Venus, and we mentioned there that up above Venus's hideously hot surface, far in its upper atmosphere which is much thicker than Earth's, it's quite possible to make rather nice floating cities, and we focused mostly on that in the episode. I also mentioned though that there have been plans for cooling down Venus, most notably Paul Birch's solar shade approach, and I wanted to focus on that and other cooling techniques today. Now, because Venus is closer to the Sun, any terraforming plan has to include not just cooling it down in the first place, but keeping it cool. Also, we've mentioned that many planets or moons could hold an atmosphere if only they had robust magnetospheres, and it's a little ironic that Venus has a very thick atmosphere and almost no magnetosphere itself, and gets savaged by atmosphere-stripping solar radiation and wind far more than any world but Mercury. Ironic, but not actually weird. See, Venus may have a very thick atmosphere, but has virtually no hydrogen in it. Hydrogen and helium being the most common elements in the universe, but rare in the inner planets precisely because they are so easily stripped off those planets by the Sun, being lighter. We only have any on Earth because it bonds to other atoms like oxygen, and that slows the loss, once the initial unbounded hydrogen blows away. Stick water on Venus and it will evaporate away, even if we magically cool it to Earth temperatures. As a result, Venus's atmosphere is mostly nitrogen and carbon dioxide, heavier stuff. So the problem with Venus is essentially the Sun. It gets a bit too much of it and doesn't turn fast enough to even contemplate a normal day-night cycle. Needless to say, this being SFIA, the concept of spinning up faster and moving away from the Sun is hardly a shocking idea. But I'm going to be making the case today that Venus is the most logical target for terraforming first, not Mars, and truth be told, the only one where it really makes sense to even try, as opposed to following different pathways of colonization or resource extraction. With that in mind, we'll mostly bypass the notion of moving it or spinning it up in favor of more near-term, easier pathways. Now there's quite a few ways to cool Venus down, and not all of them require decreasing how much sunlight Venus gets and retains, and these are of interest to us more locally in regard to Earth. As noted, Venus's atmosphere is mostly carbon dioxide, 96.5%, with 3.5% being nitrogen and everything else being the parts per million, with sulfur dioxide coming in at a very distant third, 150 parts per million, barely over a percent of a percent, 6,000 times less than its carbon dioxide content. Earth, on the other hand, only has about 400 parts per million carbon dioxide. It's not just a percentage though, because Venus's atmosphere is around 100 times thicker than Earth's, so it's got hundreds of thousands of times more carbon dioxide, helping retain heat than Earth does. If we could get rid of almost all of that, Venus would get rather livable, though civilization might cling to the poles rather than the equator, opposite of what we'd expect on cooler Mars. Now there's a lot of ways to remove that. Atmospheres are relatively light to move, compared to trying to shove the planet further from the sun or increase its spin rate. You could go faster and dirty by using atomics. The mass of Venus's atmosphere is 4.8 times 10 to the 20 kilograms. For context, while that's only a small fraction of Venus's total mass, just 1% of 1%, a 10,000th, that's about half the mass of the dwarf planet Ceres, or a sixth of the entire asteroid belt. So it's hardly trivial, but it's also already quite hot, and to move it ultra fast, we need only get it hot enough to move at the escape velocity of Venus, 10.4 kilometers per second. This involves adding around 20 billion joules of energy, or the equivalent of 5 trillion megaton warheads, which incidentally is nearly 100 times what it would take to blow Earth's atmosphere off. Sounds absurd, but as with all things, it's rather relative. You'd pay about the same energy to truck it off to other planets or habitats for use, and a lot more to move Venus. You also need to spend about 10 times that much to get Venus spinning up to a 24-hour day. No need to memorize those numbers, but we trotted them out because, as is so often the case on this show, when we discuss things that can seem ridiculously immense, it's all relative. If you're willing to remove that atmosphere, quick or slow, you are getting into the range where giving the planet a serious shove is on the table. And if we're talking about superheating gas, well, that's what we make rockets out of. Strategic application of energy to Venus's atmosphere could be used to simultaneously remove it and nudge it a little bit further from the sun or give it a decent spin. Nor do you need to use nukes. You could use a big mirror or lens to focus sunlight on Venus, or the stellar concept we've often discussed on the show and which we'll come back to. As huge as that energy requirement is for atmosphere stripping, it's only about a minute of the sun's power production. So even if you're only building enough mirrors and lenses to concentrate a tiny fraction of that solar output, it can get the job done rather quickly. Just a couple problems though. First, this is obviously heating Venus up, which is not our goal, even if it's only temporary. And second, it's taking that nitrogen along with the carbon dioxide, and we'd rather keep that. It's also a lighter element than carbon dioxide, so it will fly off faster on us. There's also the matter of where to, and if we blow trillions and trillions of tons of carbon dioxide off Venus, it's going to meander away from Venus until it leaves the solar system or gets captured by something else. The next nearest something else is Earth, and I don't know that we want to be getting extra CO2. We couldn't capture that much of it, proportionally, but as mentioned, Venus has hundreds of thousands of times more of it than we do, and we already have plenty. You can avoid Earth wandering into a cloud of liberated CO2 via timing and directing outgassing from Venus. And if you can do this, then CO2 at home isn't much of a concern anymore anyway. But at the same time, don't think of this as super high tech. As we mentioned in Colonizing the Sun, where we first discussed the stellar idea and in more detail, a stellar really is just a pair of big thin mirrors orbiting high above the sun, using the sun's atmosphere as a lazy medium. And this is handy because it means you're not mega engineering any super huge mirrors and lenses or shades. Obviously, our alternative approach is simply to shade Venus, and none of these options are high tech, just require a lot of building. What's nice about a stellar approach is that it's more compact than just big lenses at Venus's Lagrange point or in orbit, so less building. And the laser is at a discrete frequency, not just raw sunlight, so it opens up options like zapping Venus with light that carbon dioxide absorbs better than nitrogen does. Indeed, you can break that carbon dioxide up into carbon and oxygen by hitting it with ultraviolet, but that's less useful than it might sound like because carbon dioxide is a low energy state, so random carbon and oxygen floating near each other after being disassociated by UV light would generally just recombine. Ideally, we'd like to keep all that carbon dioxide on Venus, just as carbon and oxygen, so while using it as rocket propellant is an option, it's maybe not the best one. However, as we'll see in a moment, our timetable for cooling Venus down by just blocking the light off is a couple of centuries, so options on the more energetic side might be preferred simply because they save time. Building several million square kilometers of millimeter-thick shade or lens might sound like quite the endeavor, but honestly, it's well inside our modern industrial capacity groundside here on Earth. So a space-based one that was also more automated than modern manufacturing might crank that out fairly easily. Those shades might run a few tons per square kilometer, and you might need a few billion tons of them, but that is around our current annual metal production. You just need to have the capacity up in space, but power and raw materials for it are super abundant there. So it's basically how good your robots and automation are, be it shades, me, or whichever. That's why we tend to be pretty casual on the show about suggesting you can shade planets or warm them with mirrors. There's nothing high-tech about them and they aren't colossal endeavors. If I had to guess, I'd say the level of automation we'd need to set up some moon or asteroid factory that just sucked in rock and spat out millions of tons of foil a year with minimal human on-site oversight already exists. We're just not set up and practiced with that kind of remote manufacturing yet, and you'd have a lot of kinks to work out. I generally tend to figure this will end up as the preferred final solution for our own carbon dioxide concerns, so we may get a lot of practice and core infrastructure developed before we decide on tackling Venus's carbon dioxide. Also, keeping to context, throwing up a foil that's not even a millimeter thick around a planet is a lot easier than doming over a whole planet like we often contemplate for terraforming Mars, or rather, para-terraforming it. This method of shading Venus and letting it cool down was discussed in Paul Birch's 1991 paper, Terraforming Venus Quickly, and the quickly part is rather relative. Shade Venus so no sunlight gets through, and he estimates a cooling time of 90 to 200 years. He discusses some ways to speed that up, but I'll add the notion that blowing its atmosphere off by lasering sections might be the most expeditious approach, and sometimes time is worth a lot more than effort, and even more so if most of that effort is being done by stupid little robots that are being spat out by giant and mostly automated factories. The other issue that makes blowing the atmosphere off sound sane is what happens as you cool carbon dioxide down. Now, as you know, normally here on Earth, CO2 is a gas or a solid, dry ice. There's no liquid phase, but that's only true at low pressures like on Earth, and indeed at low enough pressure, substances generally do not have liquid phases at all. In a vacuum, you basically only have solid or gas. CO2 is a substance that needs pretty high pressures to have a liquid phase, but Venus happens to have that. As the planet begins cooling, cut off from light, it will begin to rain carbon dioxide, as opposed to just sulfuric acid, which is what the rain on Venus is these days. This won't be instant, indeed it won't happen until you cool to 304 Kelvin, 31 degrees Celsius or 88 Fahrenheit, versus its current temperature of 463 Celsius or 864 Fahrenheit. So this happens about halfway through or so in, when you're almost cooled down to comfortable temperatures. At this point, you will now have an ocean of CO2 accumulate on a place that's rather warm but livable already, temperature-wise. But the pressure is still quite high, and that's problematic. As it rains, that atmospheric pressure will begin to drop, and we need to keep cooling the planet more, because carbon dioxide's liquid phase is based on pressure and temperature. The lower the pressure, the lower the temperature needs to be to keep it a liquid, not a gas, and that craters out at 194 Kelvin, or negative 78 Celsius, or negative 109 Fahrenheit, and 5.2 atmospheres of pressure. Even ignoring that pressure being too high for us to be comfortable in, you can only get to that pressure by dropping to that temperature, And if you don't, if you just cool to normal room temperature, you'd have most of that CO2 still in the atmosphere and some in the new oceans of CO2 and a constant rain, at a pressure you could probably survive in with reasonably advanced spacesuits or Venus suits. To clear the CO2 out, we have to keep going even colder. We need it down to that 194 Kelvin, very nearly the record low temperature recorded in Antarctica, so that it will stop raining CO2 and begin to snow dry ice instead. It's now officially winter on Venus, and that temperature dry ice can exist at for normal Earth pressure, so the CO2 will just keep falling. If you're wondering, all that nitrogen will still be there as it doesn't liquefy till even cooler, 77 Kelvin at normal Earth pressure, and while you can liquefy nitrogen at higher temperatures under higher pressures, they are lower than carbon dioxide's, so you'll have lost all that pressure the CO2 provided before you got down to the needed temperature. Such an approach could be done on a planet that had far more nitrogen than CO2, but Venus isn't such a case. Anyway, all that CO2 falls down, and your ocean's crusting over into dry ice glaciers, but you still have that nitrogen, and it's enough that down on the frigid surface, the pressure is still too high for comfort anyway. We've got around twice the gas and pressure that we want, and still none of it oxygen. Now, oxygen itself is easy to get, most rocks have plenty of it, so it's never a terraforming issue anywhere, but all that CO2 is mostly oxygen by mass, so we'll save energy converting it. That produces heat though, and a lot of it when trying to make an atmosphere's worth. We can also start fixing that nitrogen into plants, but at the moment there is no sun and they don't care for those temperatures, so for now we'll just have to decide if we want to keep chilling till even the nitrogen rains down, or just deal with a thick nitrogen atmosphere for a while. And that is probably the better option, particularly as it will take longer and longer to cool Venus each extra degree. Hot things radiate energy faster. Of course, the moment we start warming the place back up to start terraforming, all that dry ice is going to blow off right back into the atmosphere, so we need to deal with that. We've got carbon sequestration, turning the carbon into other stuff like calcium carbonate or limestone, or we can just pave over the stuff and rely on the sheer weight of rock to keep it at pressure. This is an iffy proposition though, since you need to pile dozens of meters of rock over it to keep it at liquid at room temperature, and more like a kilometer to keep it as a solid at that temperature. It's entirely probable we'll have gotten quite good at carbon sequestration by then, and although we don't know the chemical composition of Venus's surface very well at this time, it's likely to have plenty of things like calcium or magnesium to bond that carbon to as well. Of course, carbon need not bond with anything, but by default, carbon dioxide dissociated into carbon and oxygen will form coal and oxygen. Needless to say, that's not a combination you want together at high temperatures or will just burn up. At low temperatures, we can start separating it into those two, but we need to sequester most of that oxygen into rock as well, and we've more than 100 times more oxygen in all that atmospheric CO2 than we'll want in our terraformed atmosphere. All of this is doable but takes time, even if you've got a big energy budget, because you can only use so much power at once since it will end as heat, the thing we don't want to add, so you really have to take your time doing this. This is further complicated because all that air, or new ocean or glacier, has a lot of mass, and as it drains out of the sky and pulls up in lowlands, you will begin getting earthquakes, great big earthquakes, or Venus quakes I suppose, and probably volcanic eruptions, neither of which is helping you store sequestered CO2. You can probably start seeing why the notion of just ripping the atmosphere off has some appeal. We don't want virtually any of that carbon dioxide, and we've got a lot more nitrogen than we need, and dealing with them this way is rather time-consuming. I should also note that we've got very little water right now. We are desperately short of hydrogen. However, if we've got the industrial capacity and technology for it, we can take some more proactive steps to speed this all up and do it better. Before getting to that though, we do have another brute force approach for getting that water, or hydrogen. We could of course truck it in from places like Jupiter, or send massive bombardments of comets in, but I mentioned just shooting that place with a stellar laser earlier, and that's not the only kind of beam we can blast a place with. The sun has tons of hydrogen, most of our supply of it, and it's not that hard to get the ionized stuff magnetically shot at Venus, which is a big target. We've talked about star lifting before, mostly for mining other elements off the sun, but it's mostly hydrogen you get when doing that, and you either dump it back down on the sun or take it off somewhere, and there's a lot to be said about just blasting Venus with it. I will just go ahead and name a giant hydrogen particle beam from a star a hydro cannon, because it seems appropriate. That heats stuff up too, but three main elements in Venus's atmosphere are carbon, nitrogen, and oxygen, and carbon is the lightest and the one we can blow away easiest. So if you know what you're doing, you might be able to get away with basically death starring Venus with a giant laser and hydrogen particle beam until you've got a nice mixture of water, oxygen, and nitrogen. I don't think that is a very wise approach, but it's certainly an amusing one, and might turn out to be the fastest method. Ultimately, it all depends on your technology and what your controlling factor is: time, energy, manpower, money, etc. To speed cooling, we have the option of using great big convective towers on the planet, or hanging them down off orbital rings. And you might hang a bunch of orbital rings and radiators above the planet and do some chemistry up there, extracting CO2 and nitrogen either for export or to sequester it into something that would be a solid at higher temperatures. Early on, you could actually float such factories and convection towers, as that atmosphere is very thick, rather than using active support tech like orbital rings and space towers, but it only takes about half a century to cool Venus enough you could walk around and just feel warm, and would take even less time if you're using such a setup. So at most, you'd erect the basic structures as buoyant objects initially, and begin adding in your active support as the atmosphere and buoyancy went away. Going this way, you can cool the planet faster, but more importantly, you don't have to cool it below room temperature. You might be slowed a little because running all that forced sequestration and cooling towers does take energy and produce heat, but it's a lot like running a fan and dehumidifier to cool a room. Both add more heat, but in the process of removing that heat. So you've got giant cooling towers and active support and big sequestration facilities processing out that atmosphere, which begin running as soon as the planet is cool enough that you can drop the sequestered materials back down without worrying they'll just unsequester themselves right back into CO2 and nitrogen. You might have big centrifuges being powered by beamed-in energy and hydrogen from the sun that took disassociated carbon dioxide and turned it into coal or graphite and water, or you might truck your hydrogen in from Jupiter. Ultimately, and probably in around a century, you've got a planet cooled down to Earth temperatures with the right amount of nitrogen, CO2, and water, and you can start letting some light back through your shade. You don't need a magnetosphere to protect that atmosphere though, because that shade is still keeping you shielded from the sun. But you're probably not just opening that shade, but rather altering it into a dish that's going to bounce light at another orbiting mirror that rotates around Venus every 24 hours. Just a bit lower than geocentric orbits on Earth would be, as Venus has slightly weaker gravity. That second mirror, our geocentric sun essentially, would want to be about a tenth as wide as our moon, or about 200 miles wide or 300 kilometers, not too big, though in this case not very thin at all. You want it to be fairly massive so all that light concentrated doesn't shove it away like a solar sail. Presto, you now have a perfect candidate world for terraforming, and in this case, all you've got to do is drop in the bacteria and slowly introduce more complex life and colonists as the world finishes settling into its new shape. It is likely to be fairly tectonically active for a while, now that it has oceans over some spots and thin atmosphere only over others, shifting around weight. The gravity is a little lower, and the weather will be a bit different because the sunlight isn't coming in totally uniform, but from a more point-like source near at hand. Whereas the sun is so far away, we can treat its light as coming in parallel. If you stick a light bulb near a wall, you get a bright spot on it, unless the bulb is very bright and far away compared to the size of that wall, or planet, so that every part of the wall is nearly the same distance from the light bulb, which is the case for the sun as light bulb. See the Mega Earths or Making Suns episode for further discussion of how to do geocentric lighting correctly. Back to tilt. Venus has very little axial tilt anyway, so you're likely to cyclically adjust that meal sun a fair amount to fake seasons anyway. I should note that while I just said Venus has very little axial tilt, it's actually got the most, being effectively flipped over 180 degrees, or 177.3. But from most practical standpoints, the upside down world has a very small axial tilt of 2.7 degrees compared to Earth's 23.5. You do want those seasons, as while you could doubtless genetically engineer Earth life to different or no seasons, way too many plants and animals have the seasons wired into their life cycles, so it's probably a good idea to aim for a close approximation of Earth's own. And though Venus's year is shorter than ours, if you're faking your lighting this way anyway, you can put a 365-day year into play instead if you want. As always with terraforming, you have to decide what's good enough, and which approach for getting good enough makes the most sense or least effort. Dragging Venus further from the sun, spinning it up and flipping it over seems like overkill compared to a thin, sunward shade and thick near sun. Regardless, more technology in terms of biology or sequestration or automation can all let us do this much faster. But while it takes a little more time to start terraforming Venus compared to Mars, since you've got to let it cool down a bit before you can mess with the surface, I suspect you'd be able to get the job done faster and certainly more complete than Mars. Ultimately, all you need is that solar shade and mirror system and a source of hydrogen, which if necessary can be slowly collected from the sun's own solar wind, though that would be quite slow. This gives you a nice terraformed planet, fairly quickly and also fairly low tech. We could keep going, of course, slowly spin the planet up and just remove the sun mirror and much of the shade later on. We could drag in Mercury and make it a moon, though it would be more like a double planet at this point, something we'll look at more down the road. And of course we could just dissect Mercury, reform part of it into a moon, dump the rest on Venus to add some more mass to bring it a bit closer to Earth normal size and gravity, and shove the whole thing into a counter-Earth orbit on the opposite side of the Sun. But I'd consider that overkill. As we mentioned in Springtime on Mars, you can never really replicate a planet perfectly, nor would you really want to, and so it's just a matter of deciding what's good enough. And the options discussed today in terms of shading are potentially within our capacity in this century, especially considering the necessary first step is that simple shading and everything else can be added later as it cools. We just need a robust space industry, preferably heavy on automation, and I really don't think it's a big stretch that we might have that in the 21st century. So it's entirely possible you could see dry ice snow on Venus in the 22nd century. Our hot twin might see its first winter in a mere century or two from today, even without any particularly huge advances in technology. Winter on Venus. Though until you truck the hydrogen for normal water and purge or sequester all that CO2, it's not one you'd want to introduce reindeer to. As is often the case on this show, we brought up a lot of concepts that seem so immense and challenging that they can seem almost equally difficult. A planet-sized solar shade can seem harder to build than blowing off an entire atmosphere, rather than vastly easier just by the sheer scale of everything involved. To understand how these things can be accomplished under known science and encapsulate the scales involved, or to think up new ideas yourself, it helps to have a solid grasp of math and science, and that's where our friends at Brilliant can help. Brilliant is a problem-solving website and app with a hands-on approach with over 50 interactive courses for the ambitious and curious, who want to better understand the universe around us and how it works and have fun while they're doing it. With courses focused on puzzles and entertaining examples, and with their daily challenges, you can improve your knowledge from the comfort of your own home or while on the go, and at your own pace. Effective learning is about problem solving, and Brilliant will help you learn and get practice. You'll come away better at problem solving. If you'd like to learn more science, math, and computer science, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can solve all the daily challenges in the archives and access dozens of problem-solving courses. Venus is a pretty hostile place, and the folks working to terraform it one day might be exposed to great risk, and much of humanity's hopefully bright future includes some risks and some dangerous new challenges. Next week, we'll take a look at some of those future dangers and some of the new technologies and methods we might have available to help avoid them or get people out of danger in high-tech search and rescue. Of course, one of the ways we might avoid such dangers, for those people or for those rescuing them, would be through remote piloting. And in 2 weeks, we'll look at that and some other options that may become available to us if we develop a way to interface the mind with the machine. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoy this episode, hit the like button and share it with others. And if you'd like to support future episodes, visit our website, isaacarthur.net, to donate to the channel or check out some of the awesome SFIA merchandise there. Until next time, thanks for watching, and have a great week.